Welcome to this explainer. Today we're diving into the surprisingly fascinating, super methodical process that engineers use to pick the absolute perfect material for a specific job. Have you ever wondered why a bridge uses steel cables instead of solid concrete pillars, or why a microchip uses specific ceramics instead of ordinary glass? Well, it's definitely not guesswork. It's actually a highly strategic selection process. Before a massive bridge gets built, or a plane takes off, or a tiny microchip is manufactured, engineers are faced with this massive question. How do you choose the right material? And they actually do it by treating materials exactly like human job applicants. They post a job description, they screen the resumes, they interview the top candidates, and they hire the absolute best fit for the role.
So, here's our roadmap for this hiring process. First, we'll explore the kingdom of materials. Then move to step 1, translation. After that, we'll look at screening and ranking, and finally, we'll put it all to the test with the heat sink test.
All right, part 1, the kingdom of materials. We've got to start wide here, looking at the sheer scale of what's available to us. Engineers actually use massive databases for this, like the Cambridge Engineering Selector, or CES, and online spots like MatWeb. To make sense of all this data, they use a really strict taxonomy. They categorize everything into a hierarchy, funneling down from broad kingdoms and families, right down to classes, subclasses, specific members, and then finally, their exact, measurable attributes. Now, you can visually trace this whole hierarchy. It's like a giant funnel. You start at the kingdom of all materials. Then you branch into a family, like metals, then down to a class, like aluminum alloys. You keep drilling down to a subclass, say the 5000 series, until you hit a specific member, like 5083H2. And boom, right there you arrive at its precise attributes, its exact density, modulus, strength, thermoconductivity, and yep, even its cost. It's how engineers know exactly what they're working with. This really brilliantly illustrates that material selection doesn't happen in a vacuum, It's a complex interplay between 4 crucial pillars: the material itself, its shape, the manufacturing process, and most importantly, its ultimate function. Notice how function sits right at the top there? That's the primary driver. The function dictates the material, but hey, the material also limits the process and the shape. So it's this continuous, interconnected loop.
Moving right along to part 2, step 1, translation.
Think about it this way. If you were hiring an academic coordinator for a university, you wouldn't just look at a crowd of people and guess who's best, right? No, you'd write a precise, detailed job description to make sure the exact right candidates apply. Just like a real-world job ad lists minimum qualifications like, say, a bachelor's degree in electrical engineering, and specific location constraints, engineers have to do the exact same thing. They've got to convert the expected performance of a part into a measurable, numerical set of properties. Basically, they're writing a job ad for the material. So the crucial point here is breaking the engineering problem down into 4 translation attributes. First up is the function. What does the component actually do? Second are the constraints. What are the absolute non-negotiable conditions? Third is the objective. What exactly are we trying to maximize or minimize? And fourth, the free variables. What parameters are we actually allowed to change to solve the problem? Let's look at a real-world example to see how we build this job description. Think about a massive suspension bridge. If we focus entirely on those vertical suspender tables holding up the roadway, how do we write the material job ad for those specific cables? Well, here we see the translation in action. The function is straightforward. It has to support a heavy tensile load. But the constraints, those are strict. We have a specified length, let's say 2 meters, and it absolutely must support tensile stress without yielding. That means its yield strength has to be strictly greater than 500 megapascals. Our objective is to minimize mass, so we're looking for a density of less than 10,000 kilograms per cubic meter. And the free variable? The material itself. That's the one thing we get to choose to make all of this work.
All right, part 3, screening and ranking. Now, screening is absolutely ruthless. It is all about shortlisting candidates based solely on those non-negotiable constraints we just talked about. If our job ad says we need a Young's modulus of greater than 100 gigapascals, any material that falls even slightly short is instantly disqualified. It's literally like a job candidate showing up to a corporate interview in their pajamas. They're fired before they even sit down.
And this is where the process gets beautifully visual. Engineers use what are known as Ashby charts as maps to instantly screen materials. By plotting something like strength against density, where each bubble represents an entire class of materials, they can just draw a line.
If our constraint requires a highly specific strength-to-density ratio, everything on the wrong side of that line, like woods, foams, or unalloyed polymers, is immediately visually eliminated. It saves a massive amount of time.
Once we've shortlisted the survivors, we rank them, and this ranking is driven by our objectives. Which of these surviving materials minimizes mass the best, or maximizes strength the most? But it doesn't end there. Step 4 is supporting information. The top-ranked candidates get evaluated against practical, real-world facts. Is it actually available in our region? Is the cost within budget? Is it eco-friendly? Can we even process and manufacture it easily? The winner of all 4 steps, they get the job.
Which brings us to part 4, the heat sink test.
Let's put this whole strategy to the test with a microchip that operates at incredibly high temperatures. We need to design a heat sink that pulls heat away and keeps this chip strictly below 200 degrees Celsius. In the world of tiny electronics, that is a massive, incredibly difficult engineering challenge.
By translating these requirements, we establish our extreme constraints. It has to pull heat away, sure, but because it sits directly on a microchip, it absolutely must be a fantastic electrical insulator so it doesn't short-circuit the whole board. We're talking an electrical resistivity of less than 10 to the 19th microohm centimeters. And the objective? Maximize the service temperature. Our free variables here are the geometry and, of course, the material.
So, out come the selection charts again. By plotting thermal conductivity on the y-axis against electrical resistivity on the x-axis, we map out our applicants. Metals up at the top left, great thermal conductivity, but terrible electrical resistivity. They'd totally fry the chip. Polymers on the bottom right, great insulators, but terrible at conducting heat. They literally melt the chip. But if we visually pinpoint the exact tiny pocket in the top right that satisfies both extreme conditions, boom, there they are. Technical ceramics, like aluminum nitride and silicon nitride. They're the only candidates tough enough to survive this grueling job interview.
So whether it's the massive steel cables on the bridge you drive over every single morning, or the microscopic technical ceramics silently pulling heat away from the processor inside your phone right now, every single material around you is a survivor of this exact 4-step screening process.
I really hope this explainer has completely changed how you look at the engineered world. It's a world where absolutely nothing is left to chance, and every single component has truly earned its place. Kind of leaves you wondering, doesn't it? Next time you pick up an everyday object, ask yourself, what invisible, rejected materials applied for that exact job and failed? Thanks for hanging out with me for this explainer, and definitely keep questioning the world around you.